Okay. I was asked a very good question at the end of that last lecture, and I think I gave a needlessly complicated answer. So I want to answer that again, since it's question time. So just to remind you of the question. The question was that I gave the example of QCD and dynamical symmetry breaking. Here is alpha QCD. On this axis I'm putting the scale. And we said asymptotic freedom was the key, the beautiful slow growth of this coupling was the key to understanding why the bound states of QCD, in fact all of the interesting phenomena of non-perturbed QCD happen at low energies, even if you start at some high scale. So, I started my story at that scale. And here is, let's call it 4 pi or something. Okay. So I started at weak coupling, and the theory started because of asymptotic freedom, or infrared non-freedom, it started growing. And let's say there's some value of order 4 pi, let's call it alpha critical. At alpha critical, let's say that alpha critical is the value of the coupling. The theory becomes so strongly coupled that all the quarks get combined and they form bound states. Okay? So therefore, at alpha critical, we form we confine quarks. And this is the mass of the atoms. And it's also what we would therefore call lambda QCD, roughly speaking. Okay? That's the operation of lambda QCD is just this is the scale in which all the masses that QCD produces through dimensional transmutation take place. And let's just define it in some number that is of order strong coupling. And we understand why this scale massive hadrons of chiral symmetry breaking in this other universe, the mass of the W's. We understand why it's so much smaller than the gut scale because of the form of this beta function, of the growth of this. In fact, the beta function, we draw something a little more abstract, where these are the axes. Okay? Then the beta function, of course, famously looks like this. And it's like g cubed minus g cubed, and then order g to the 5th. And so it has this kind of a shape. And what this says is that, of course, in the infrared, as mu goes down, you grow. If the beta function is negative, it means you go to larger and larger coupling. Sorry, I should have written alpha. Alpha squared. Cubes. Alpha. To be consistent with that. You go to larger and larger alpha, and here's alpha critical. But there's something special here that when you're at small values of alpha, the beta function is also small, and so you tend to run very slowly. That's what I was saying. You tend to run very slowly for small values of the coupling, and you spend a lot of time. In other words, you spend a large number of decades of mu at weak coupling, and then slowly, once you exit weak coupling, you pick up, and things happen very rapidly as you move down in mu. Things happen very rapidly. You get to this scale, and boom! Maybe this is the physics that happens. And the question was, I seem to have changed this picture in order to talk about these large anomalous dimensions. I changed the picture so that over a large hierarchy between n gut and coming down, here's n gut again, you're spending it, you're doing this, okay? So this is some alpha, let me call it alpha star. And here, the picture that I want to consider is this is the alpha critical. This is the basic idea of again, the generic brand, the generic name of this kind of phenomenon is called walking technicolor. but again, it has many incarnations that one can contemplate. But the basic idea is to contemplate that you don't start from zero coupling or small coupling and keep doing this. You have strong coupling, but just not strong enough to form bound states. So the bound states still form here. Okay, so this is the M of the hadrons. And chiral symmetry breaking and all of that. But you spend a large number of decades of energy just going very slowly like this. Now, why is this a plausible picture? This picture we can calculate because it's just QCD and piecing together experimental data on confinement, on the fact that we do confine and so on, and then perturbative calculations in QCD here, we can piece together that this is the story. Here, I have a justification for this story if the world happened to have QCD. In a theory which is strongly coupled but not a copy of the real world, what is the plausibility of this picture? That, I think, is the question. And the fact that we can have a large hierarchy at least is at least, you can see that it is possible, but why is it plausible? So we again try to draw a beta function of alpha, but this is alpha of some theory which is not QCD-like. And, but we want to play around. We're starting off, so here's alpha star. Here's alpha star. Perturbative values are out here. I'm not even going to think about being there. And here's alpha critical. So they may be comparable, but one is smaller than the other. And we can imagine, so now, I don't know what this picture looks like, but I can at least look at what would be typical behaviors that I could contemplate, okay? So I could contemplate this. That's possible. Let's see what would happen in this case. In this case, because the beta function is positive, it means that you're moving towards, as mu goes down, it means that you go in this direction. So if you started here, if you started at alpha star for some reason, you would rapidly go off in this direction towards small coupling. And then maybe this thing would turn around, or who knows. Okay. Well, that's not good. So there is a possible beta function that would not help to give you this picture. There's another one I can do. I can do something like this, and it would still have the same feature. Okay, and I could have something that looks like this, and indeed, what it says is that you rapidly do flow here. But if you're rapidly flowing to alpha critical, then this is not the correct picture. The picture looks more like this. Then this is M gut. You start at alpha star, or somewhere near alpha star, and you rapidly blow up, and this is alpha critical, and here are the massive hadrons. This is an entirely plausible picture, but it's not the one we want. And the same is true if I did this. However, here is an entirely plausible, one of the things that's entirely plausible in this picture is that you cross the zero axis somewhere, okay? So an entirely plausible picture is something like this. Right? That's also plausible. And you see, it looks sort of qualitatively like this, except shift it over. Now in this case, I define alpha star to be the crossing point, okay? When alpha star is what's called a fixed point, because it says that mu d mu of alpha is beta alpha. And at alpha star, it's 0. Okay, so the coupling is not run. But I start somewhere near there. I don't start exactly at alpha star. So let's say I start a little bit above alpha star. But because the beta function is small here, even though the coupling is big, it's easy enough to generic shapes of RG flows, it's easy enough to see that it's possible for the beta function to be small. Which means that when you're here, you're moving only slowly. So for a large hierarchy, the coupling is the solution to the equation of the beta function is just creeping along. But eventually, it slowly makes its way out. And eventually, it gets away from being zero. The beta function becomes negative and sizable. And then it rapidly does its thing and ends up hitting alpha critical. And that's what this picture is. Okay. So it is not that this is guaranteed to be true, but we find it incredibly plausible that somewhere in the space of all possible strongly coupled theories, that something like this could happen.
And one question, I mean, it should go near alpha star, but it cannot cross it, right? I mean,
no. So you wouldn't want to start your running here. If alpha at the gut scale was, say, here, then you would end up getting stuck here, right? So you see, there are sort of some discrete choices that nature had better make in that other world, or if this is the theory of the Higgs center that we're talking about, some strongly coupled Higgs center. It has to make some choices, but they're not what you would call very fine-tuned or contrived choices. They're rather bold and generic possibilities. That's it. Now, that still leaves us at the end of the lecture with the question, okay, that's a very nice story. How should we explore the fact that I want this, I want some other things, I have a long list of things I want, and we want to get it all together. And that's the framework I wanted to at least sketch for you. But coming back to question time.
So again, the reason we wanted it to grow almost don't say it is because of the reasons of the pictures you made with anomalous dimensions and stuff, right? I mean, it's because
the reason that we wanted it to not. So two things. The reason that we do, but again, for the record, the question was, what is the reason that we wanted it to be strong and not growing? And the answer is those two things. We wanted it to be strong and not growing because we wanted to get these large anomalous dimensions from class, things that look schematically like integral the log mu from some low scale mu to some, so let's just say, m hadron. Where I got the region, so roughly a large region in which the coupling is fixed, we could have order alpha over 4 pi or something. And this could be order 1. And then this would turn out to be an order 1 power of m gut over m hadron. So we wanted to get large anomalous dimensions. So that's one thing. In other words, what these large anomalous dimensions do is they take the very small couplings that look like this and they make them more important in the infrared than you would have thought by just pure dimensional analysis. A strong coupling, this canonical dimensional analysis is not as useful. What really matters is the true scaling dimensions, which are the sum of some canonical dimensions and some anomalous dimensions. Okay. In condensed matter physics, we would call those critical exponents. But the other thing this picture helps to explain, the fact that the beta function looks like this, is that this itself is what we want, but this is an output of some beta function that the theory would have. And we need a picture of beta function that looks like this to explain why there's such a, even though you're within striking distance of alpha criticals, where you form bound states, you're quite close to it already at the gut scale. So why does it take so many decades of energy before you actually form bound states? And this is very beautifully explained if you have a picture that looks like this. Okay. Because even though the coupling is big, the beta function is small. And so the beta function is telling you how rapidly the coupling changes. So while the coupling is big, the coupling itself doesn't change. The rate of change of the coupling is small. Okay, yeah.
Yeah, I wonder if taking the 3 generations.
4 generations.
Okay.
Yeah.
I wonder if like we have to introduce new scales alpha stars of we just have the one scale.
If you, so, let me see if I understand the question. Are you speaking about a 4th generation model? Or I mean, a model with 4 generations of, oh, you're saying because we have 3 generations, the usual ones, and now we have this Technicolor sector, which, and it needs its own forks,
So
which is like a 4th generation.
More alpha star scales. Or
Yeah, so let me state that. So when I describe this story to you, I describe a story where QCD played the job of spontaneously breaking chiral symmetry and giving mass to the W boson. And that was an analogy, or if you want, it was true for the aliens. Okay? But then, if the moral of the story is, and this is a variation of this, where I just showed you how one could even generate substantial fermion masses like lepton masses. In the same story I was telling you, you could also end up, if it wasn't QCD, but some deviation from QCD which looked like this, then one can imagine getting even sizable lepton masses because these operators could be more important in the infrared than you would naively think. So that's one statement. Now we say, how does this moral of this story carry over to the real world? Okay, what could be happening in the real world? And so in the real world, we have to say that it's not QCD. So we have QCD cross Electroweak. We are not going to use QCD to generate W and Z masses, otherwise it would have generated them at order of the GeV scale, which is, of course, not what happens. So we have to assume that there's a new strong force. Let's call it Technicolor. Again, it's the easiest thing to say, and it is a politically loaded statement. So, that is, you'll get strong reactions from people if you tell them this. Some will love you, because the band of brothers and sisters is so small, and others will have only contempt for it. Okay, so, but I can't think of a quicker word to say. You need a new strong force. Okay? And in fact, it's sociologically interesting because you'll find that people who don't want to say the word Technicolor but still want to talk about it will use many other words: dynamic symmetry breaking, new strong sector, many words, so they don't have to say it. Okay. Anyway, fine. So there, I'm just saying it. Technicolor, let's put prime on it because it could be some variant in many different possible variations. New strong dynamics of some sort. It's not this force, it's some new strong force. Now this, we have standard quarks which carry both of these, and we have standard leptons. Which carry this, and of course we have 3 generations of these. And if I understand your question right, then the question is, we need at least a new generation of this. Or something like a generation. It doesn't, who knows whether the details, we don't know the details, whether this is exactly a 16 or something. We don't know the exact representation. We don't know what this is. This a gauge theory? Is it some other kind of strongly coupled theory? We don't know the exact details. But let's say it does have to have some matter. So I'd rather say there's matter, and this arrow here, this line just says the matter is charged under whatever this Technicolor force is. Okay, it feels this Technicolor force. And somehow the matter, what's crucial about the matter, is it's also charged under Electroweak. So that once this undergoes some spontaneous symmetry breaking and some critical coupling, it generates masses for the W and Z. And because this thing does its job, not at GeV scales, but TeV scales, we end up with MW of order 100 GeV. Okay? And we end up with hadrons, which are of order T. So what's the new physics in this story? The new physics is go look for every other. This thing has eaten 3 hadrons, which are the 3 pions. I should say, it's eaten 3 technihadrons, the 3 pions of this thing. But there should be, those are pions, that's why this thing looks like. Where are the rest of the technihadrons? They're somewhere up there at the TeV scale. I'm being sloppy about any of these numbers, but so far we don't know. We're even trying to figure out what direction to go rather than having written down a model. Nothing is perturbative, so I don't just say, tell me the field content, tell me the gauge group, let me go. We don't even know how to start, but nature might be doing it. So this is the picture. Now, I think this is what you meant by the word 4th generation, perhaps. But I'm not sure. Is that it?
What I mean is like, we are enlarging in this strong sector, we are enlarging the gauge group.
Yeah, in the sense that this might be a gauge theory.
Okay.
Right.
Like SON.
Yeah, maybe it's SON, maybe it's SUN.
For example.
For example, SPN.
And through the spontaneous switch breaking using the masses of fermions, right?
Yes, the spontaneous symmetry breaking breaks the chiral symmetries of whatever fermions are here.
So we actually need 3 of these groups for every different family.
No. So the question is, do we need, does this matter have to come in 3 generations? Now, in the original Technicolor, the capital T, Technicolor program, eventually the idea of how you give masses to ordinary fermions, okay, how do these guys get masses? The story of how these guys get masses was ultimately pursued in various ways, and in one such approach, you ended up having 3 generations of technifermions to match the 3 generations of ordinary fermions. But that approach did not use this kind of partial compositeness idea. So the original Technicolor, that's why I'm being careful to say that I sort of talk about Technicolor with a small t. And indeed, maybe one has to, I'm saying it to say, I'm using that language only here to say it quickly, but generally one should just, of course, it's true. It's really some sort of generic, strongly interacting theory. But a crucial thing that I have, an attractive thing that I'm pointing out is this possibility, and this was not what was originally pursued in Technicolor. And in fact, it was later introduced into Technicolor by David B. Kaplan. There are many David Kaplans, and one was David B. Kaplan. And he introduced the idea in Technicolor of this idea, which we call partial compositeness. And it was almost completely ignored. And partly because the large anomalous dimensions needed to make the idea give you sizable fermion masses, like the bottom quark mass thing, it seemed rather implausible that light would be so good as to give you large anomalous dimensions of that magnitude that would make everything okay. But the idea came back in RS. So RS, I'll again just sketch the beginnings of it and give you the appropriate references. But RS is some geometrization of this story. And in that geometrization, it wasn't, when RS was first done, and to some extent, it was a little not obvious exactly how everything matched up between the RS description and this description. But the thing that was easiest to do in the RS geometric description was this, but in some disguised way. which made it seem very attractive, very natural, and indeed it is attractive and natural. And only at that point did this old idea of David B. Kaplan's become popular. Up to that point, the Technicolor people were pursuing a very different approach, qualitatively different approach to giving fermion masses. And in the qualitatively different one, which I think was called extended Technicolor, you had several generations of matter and so on. Okay, so that's one distinction. I've lost it. There was one other point I want to make about the RS switch. So, there are two approaches to trying to deal with this sector. In our thinking so far, it's like a black box. It's like, I just have these properties. And indeed, the field split into two directions. There are people who really want to write down which gauge group this is, what matter content there is. In other words, they want to write down something pretty explicit. This is a very high standard, because you write it down, and now what do? Maybe you get a big computer and you try to simulate this theory, which is very challenging. Or you guess what the theory does. You write it down and then you make a guess as to what it does. Or you use various analytic approximations which are not in control, but you hope for the best. That's one direction, and it's a reasonable direction given the difficulty of the problem. Another direction is to try and find a new parameter to expand it, okay? Which is not weak coupling, asymptotically free, none of that. So indeed, the attempts to even conquer QCD. QCD has a strong coupling where it matters most. You're trying to describe the happens. And in QCD, long before Technicolor, a little before Technicolor, Tufts already was looking for a small parameter which would be valid even though the coupling, the naive coupling constant was big. And that led to the 1 over n color expansion. This gives you tremendous insight. Of course, in the real world, n color is 3. So you at least hope for qualitative insight. This gave tremendous qualitative insight into the nature of strong interactions, both of this type and of this type. But it did not give a calculational scheme. In other words, even this expansion did not allow you, calculating the powers of this, did not allow you to calculate real numbers the way I do in QED. I calculate G minus 2 of the electron in 3 loops. That's not the way this thing works. Okay. Not because 1 over 3 is big or small. Actually, in chiral perturbation theory, when people study chaos, which they do quantitatively, the expansion parameter is also about 1 over 3. And they just don't get high precision, but they can calculate numerically. But here, it's not well defined. Just this structure is not, this perturbative structure is not enough to actually calculate. If you want, and so part of this whole thing, conquering strong coupling, this is, however, a minimal lesson that everybody has to learn. In Coleman's Erice lectures, you'll see that described as a quick read. It's an elegant and quick read. I like Witten's, even more than Coleman's thing, I like Witten's introduction to his paper on large N baryons. So before he does baryons, he describes mesons and blue balls. I think it's some nuclear physics paper. But the introduction, he describes the basis of mesons and blue balls. And you can see the power of detective work that gives you this expansion. But this is still not quantitative. So the world needed one more small parameter somewhere if you wanted to make it quantitative. And that is, so that is exactly what ADS-CFP provided. Now, if you read the standard ADS-CFP literature, you will have to look hard to see this thing phrased in the way I'm about to say it. But nevertheless, what I'm saying is true. That is, there's a historical directive. ADS-CFT came out of nowhere, came out of detailed string theoretic calculations with brains and strings and a lot of scattering thought experiments and so on. So the historical thing had a lot of details that only over time you realize which ones were important, which ones were not. Okay? But now we can say it in one small sentence. What is this? And the answer is, it introduces one new parameter. Okay? I'll tell you. Just like this beautiful set of insights can be ultimately, when you understand what the hell you're talking about. It's one new parameter, but this is one new parameter which you can work in. And you know, when you discover Feynman diagrams, you start working in coupling G or coupling alpha or something, and you find this beautiful graphical world that opens up. It's not that space-time looks very graphical, but suddenly you find yourself drawing elegant diagrams that look like this, and you know, and these graphs have a life of their own once you get used to them. When you did large N, there's a new something emerging from this picture that you start to see. You start to see these bluebonic diagrams, which are, however, these are the original diagrams. And but in perturbation, the perturbation theory is becoming strongly coupled, so there are gluons going everywhere. And it's an amazing fact that the picture that emerges from the large N expansion is that these gluon diagrams end up being sheets. They turn into sheets. It's like somebody's wearing a knitted sweater. All the gluons are like the yarn on the sweater. But somehow then the sweater can have interesting shapes. That there can be classes of Feynman diagrams that look like the torus. There can be classes of Feynman diagrams that look like a sphere. If you look inside very carefully, you'll see, oh, right, I mean, the fabric of this thing has got this structure. So emergent from the analysis, you suddenly find, oh, the diagram, the classes of Feynman diagrams that look like this are 1 over n squared smaller than the classes of diagrams that look like the sphere. And this is the source of your insight. Okay, then you try and figure out which physical effects happen at this order, which physical effects happen at this order, and you get enormous insight into how the theory works. Okay. Just as an example, yes, I don't have to repeat. Coleman and Witten wrote a paper proving in large N, it's hard to prove anything in strong coupling, but they took an input. They said, suppose the large N theory confines. They don't prove it. They put that as input. They prove that if large N QCD confines, then they prove that it breaks chiral symmetry. Because it is logically possible to confine and not break chiral symmetry, or to confine and break chiral symmetry. And they prove, and it's even possible to break chiral symmetry and not confine. They're logically independent. After all, the linear sigma model doesn't confine, but it breaks chiral symmetry. So these guys, they use the power, just to show you the power of this. This seems qualitative, but qualitative things can give you qualitatively important things that you care about. And often the rest follows by dimensional analysis. Oh, you break chiral symmetry? I wonder where you break it. Well, probably at the confinement state. So you can at least order 1 numbers times confinement state. So it's a very powerful thing. Now, here's what happens if you take this expansion. I haven't told you what delta is yet, but I'll tell you in a second. But what if you take this expansion and this expansion and you put them together? Then, amazingly, you get not just a qualitative guide, although it is qualitative at least, but it's even quantitative. You get quantitative calculability. That's incredibly powerful, right? That's like, now I'm doing, it's like doing chiral perturbation theory again or something. I can calculate stuff because I have such a deep insight into the strong dynamics. Chiral perturbation theory is the calculations that you do for soft pions. Even though the quark theory is strongly coupled, the effective theory called chiral perturbation theory is got enough control with a new small parameter known as E squared over 4 pi f pi squared. Or if you want, E squared over lambda QCD squared. This becomes your new small parameter, even though the naive small parameter is good. So that's an incredible breakthrough that you have actual numerical calculability in this expansion. And if you give me a few inputs, just like I said here, if you give me a few input statements, either because you conjecture some strong dynamics with these properties, or you happen to know some strong dynamics which has some input properties, then you can run with it and calculate a lot of other things. Not even qualitatively, but quantitatively. And you can ask, just like here, there's some emergent. I start with this, I end up with the graphs, a world of graphs. I do this, I end up with sort of, the graphs end up knitting sweaters of various types. Okay? And what happens when you do this? What is being pulled out of the air by this expansion? And the answer is extra dimensions. Okay. That the graphical world on which these things lives in higher dimensions. So tomorrow I'll sketch where, how could that happen? But let me just say what the delta is. If you look at operators, it's in fact the reason I bothered to say the word normalization group in these lectures when presumably you're seeing it in other courses and so on, is because this notion of scaling dimension is very, very important. This delta is actually a scaling dimension. Okay, so that's why I'm bothering to say the word normalization. So let me say what we're talking about. First of all, if you write gauge invariant operators, O, where these are, composite. For example, psi bar down mu psi, q bar down mu q. These are composite operators. They have different spin and different isospin and so on. But the one thing is they're gauge invariant. That is, the colors are contracted. Okay. Of course, there are many, many composite operators. Now, in a theory with a large number of colors, there is an atom. There is an atom that you can point to. Because obviously, two operators multiplied together is another composite operator. These are local. These are local. Okay, so the x here is the same as the x here, or possibly infinitesimally different. That's it. Okay, that's all I'm talking about. But obviously, the product of two such things is also a local operator. So when you see any operator, you can always ask, does it have divisors? Meaning, can it be written as, if I give you this, can it be written like this? Now, in a large N gauge theory, there is the sort of what are called of course, you have to form color singlets. The very minimum thing to be gauge invariant is to at least be a color singlet. Okay. Anti-green, green, and so on. So the minimal color singlets operators. The minimal color singlet operators are the ones for which this is a minimal color singlet operator. It cannot be factorized as two other color singlet operators. So minimal color singlet operators, you can draw a different type of spectrum than you're used to drawing. You can draw the scaling dimension The scaling dimension is the sum of the engineering dimension, the canonical dimension, and the anomalous dimension. And remember, if you're exactly at a fixed point, then the alpha here doesn't run, so this is just a number. Sorry, this becomes just a number. Okay, so if you add it to the canonical dimension, you get what's called the true scaling dimension, not the one that you get by doing dimensional analysis, but the true scaling dimension. And you can list all the, of course, there's an infinite number of minimal color singlet operators, and the n is very large, but it's a large set. It's a large set. And you can list what they are. So here's one, here's dimension 1, okay, and 0. These are all tend to not be realized, but then you have some list. So the spectrum looks like this. Okay. If you want, you can write the Lorentz representation of the operator here, or something like that. So you end up with something like this. This is not your usual kind of spectrum. It's because this is not mass. This is the scaling dimension, which is the dimensionless number. But you can write this. Now, in a particular kind of strongly coupled theory, it is possible that there's a gap. So for this, you need mathematical aliens. They come in and they say, I wonder if there's a gap in the spectrum. You might say, this is not the kind of gap I care about at the LHC, but this is the kind of gap that a mathematician might be interested in. Because so one possibility is there's some order one operators, some finite number of order 1 operators, and then there's a gap, and that gap I'm calling delta, and that delta is this. So it's remarkable. We already know some operators. So there's a operational way to proceed if you're trying to use this as a tool for trying to figure out what is basically possible in terms of the Higgs sector and the real world, which is, we already have some operators that we want to have low scaling dimension. For example, this QQQL, whatever replaces this in the true Higgs sector, this is a kind of composite operator. If it has a very large, much larger than order 1 scaling dimension, I'm dead, because then this is going to become incredibly small in the infrared. So I need it. I need this operator to have order 1 dimensions at the very, very least. So it better be one of these guys. And you can see it's interesting because it has, this is spin half, so this better have the next, I don't care what it's made of. Scalar, quarks, real standard, Fermi, spin half quarks, whatever. But the entire operator has to have spin half, so, right? So that'll be some spin half guy. And it has to be here. So there is a set of operators that whatever idea you're pursuing in this Technicolor strong dynamics game, you want some order 1 dimension couplings. You can't live without. And then you can hypothesize, if you want to make use of this expansion, you can hypothesize that all of the operators that you don't want are also at high scale dimension. This is a maximally optimistic viewpoint because that means that the effects of such operators, even if these operators are turned on in the effective Lagrangian at the gut scale, by the time they get down to the weak scale, they are irrelevant. So it's a nice fit with what we want, which is to keep the fewest moving parts, even in our thinking about strong dynamics. Once you have this separation delta, ADS-CFT tells you exactly how to do this expansion. And it ends up giving you an expansion in this extra-dimensional sense, which I'll point out here. But this is the powerful and exciting direction. In this way of thinking, I don't even have to tell you which is the SUN gauge group, SON gauge group, SPN gauge group. I don't even have to tell you that. It may not even be a standard gauge theory. It just has to be some kind of a strong dynamics theory which has some sort of large N expansion. And then, boom, we can at least play this game. And in this way of thinking, you don't have to look inside and say, all I need to know about this operator is that it is overall a fermionic operator. I don't need to look inside and say it's made of 3 quarks. Maybe it's made of a scalar and a quark. I don't need to know. In this expansion, you don't have to tell me that information. I can calculate anyway. This is exactly like the Cairo-Lagrangian, if you know Cairo-Lagrangian for pions. The Cairo-Lagrangian was useful even before the discovery of QCD. I didn't need to tell you that the pion is made out of quarks and gluons to use a Cairo-Lagrangian to calculate, numerically to calculate cross-sections for pi-pi scattering at low energies. Similarly here, you bypass this business of trying to figure out which gauge group the Technicolor theory is. That's why it's not now called Technicolor, this direction. Because you just say, that's a black box, I don't care. I have my expansion parameters, I can calculate, just like in Cairo. Yes?
No, please.
So in lectures, you have a theory with 3 massive bubbles, and you use this sort of lecture to write a theory with SU2L gauge rates. Am I correct in saying that if the masses of the 3 bubbles were different, it would not be possible to use a Stuckelberg trick to write something with SU2L gauge variance?
So the question is that when I use the Stuckelberg trick, I started with a theory which had 3 degenerate W bosons in what now we would call unitary gauge. After we see the Stuckelberg trick, we call it unitary. So what experimentally would be 3 degenerate W's gives rise, certainly it's consistent with the Stuckelberg trick, and that's the one I did. Suppose that 3 W's were not degenerate. So I had written down 3 W's. So if I had written down MW1 or plus minus squared W plus minus squared plus MW3 squared W3 squared. If that was my starting line on lecture 1, and this were not equal, then would the Stuckelberg trick still work? And the answer is yes. However, the simple form of the nonlinear sigma model that I got would not have been, so it would have changed. If you follow the Stuckelberg procedure, it would have worked, but I wouldn't have got the same simple thing that I got at the end. So there's a general procedure for doing Stuckelberg, which by cleverly choosing that other example, I could do something similar.
So, in what sense is custodial symmetry an accidental symmetry?
Ah, good. So the question is,
if you can do it
yes.
using that
So, state the question again. When I pursued the trick where they were equal, I did the Strickleberg trick, and in the end, we said, okay, after all the manipulations, we can still see it in the chiral Lagrangian, or in the nonlinear sigma model. We can still see in the nonlinear sigma model that you have to have, that the nonlinear sigma model, mu sigma squared, trace, or whatever, had SU2 left, cross SU2 right, spontaneously broken to what I call SU2 custodian. And so, it looks like the Strickleberg trick somehow led to this, but actually, I don't think that's the right way to say it. Given that I started with custodial symmetry, given that I started with 3 equivalent W bosons, the Strickleberg trick ultimately led to a system which also had that symmetry. And so, if I started without this degeneracy, and I followed the appropriate Strickleberg trick in that case, I would find that I didn't have this at the end of the day, that the spontaneous symmetry breaking instead just gave me U1 electromagnetism, or U1 that I need for electromagnetism. But it didn't give me this bigger symmetry in any way. So, in a sense, a lot of what I've been doing are like special case examples which fortunately apply to the real world with approximation and are very simple to do. But a lot of the examples I'm doing for you, every trick in the book here, is often the simplest example of its type. And it's only to whet your appetite to say, once you learn the more general case, how would you do it? And occasionally, as you're playing around with different aspects of beyond standard model physics, you will be asked to, you will ask yourself, how will I do the Strickleberg trick for this other case? And the answer is it's going to be very messy, but there's a procedure, and I'm not telling you how to do it, but you can learn how to do it now that you can Google on Strickleberg.
So nature could have non-linearly realized SU2L without custodial symmetry?
Absolutely. Nature could have realized SU2 left without custodial symmetry. And as I showed in this example with Electroweak triplets, maybe it has, but just a small break in custodial, I suspect. But as far as your qualitative question is concerned, it's possible. It's possible.
So you have these operators at the gut scale which then generate your lepton and quark masses. Why? Because this Technicolor is one which has a Higgs, right?
Now, yes, so en route to phrasing your question, you asked an important. In my desperate attempt to do everything very, very minimally, I've said something which might be in contrast to what you might hear in the outer world. And I did it by taking a very clever lawyer-like approach. So let me clarify that, and then you can ask me the rest of your question. Which is, in standard Technicolor circles, people contrast Technicolor to the standard model Higgs by saying that Technicolor doesn't predict the Higgs. It's a so-called Higgsless theory. And let's see why they say that. They say that because this is so-called sigma. So indeed, what we really mean by the Higgs, when we use the word the Higgs, is we mean the linear sigma model, that thing which has those 4 components. And we mean the normalizable theory, where this, by which I mean that we have these phi's in some way, right? One of them turns out to be the Higgs, and the other 3 are massless Wilson bosons, at least until you couple it to the W's. And then there's a big gap. There's a big gap until you get to the next particles. Okay? Yeah, that's big. This is what we normally mean by the standard model Higgs. That if even of course, standard model, in principle you'd say textbook Higgs, there's a gap up to infinity, but even when we apply the words in more practical settings, we mean that the Higgs is one of these things, there are some pies that get eaten, and they're all much lighter than the next particle that you're ever going to see. And really what's going on in the standard old Technicolor, the one that is literally copying the moves of standard QCD, is that you have a spectrum that looks more like this. There are still the massless pies. Okay. Indeed, the same quantum numbers as this H, just say the quantum numbers of the vacuum, you can indeed see something vaguely like a Higgs. It's a sigma. It's much heavier, and so once I gauge the theory, the W mass goes down somewhere. Okay, these get crossed off. But while in the standard picture the Higgs is comparable, here this thing, my would-be Higgs, is far heavier and decays more rapidly than this. But indeed, if you just take the standard model Higgs and you go to the part of the parameter space where the Higgs mass gets heavier and heavier and heavier, it looks a lot like this. So, even though many people call this Higgsless, they call it Higgsless because it's not like there's the Higgs, there's the W, and then there's a big gap to the next thing. Where the sigma occurs, so does the techniproton and the techni-rho, and there's a whole bunch of junk that comes at the same time as the sigma, or the would-be Higgs. So there's no isolation of just the Higgs and the pi. There's no isolation like that. But this is still semantics, because it is really true that if you take the standard model Higgs, which has a parameter in the standard model called mh, or if you want, lambda, and you make this bigger, as this goes up, and you look at the behavior of the Higgs, it starts to behave more and more like the sigma. So, one way to say it is that the standard model Higgs, when it gets heavy, the standard model renormalizability, as I explained in terms of Landau poles, the standard model becomes extrapolatable to not very high energies. You cannot extrapolate the standard model with a heavy Higgs to very high energies. Some new physics has to come in. And that's the physics of these techniprotons and techni-rhos that comes in. Now, that was by way of just explaining this statement, to what extent you want to call this the Higgs. So often when people say the Higgs, they mean the version of the story where the Higgs is light, not the version of the story where the Higgs is heavy and wrong. But that's only the prelude to your question.
Okay, I mean, I was sort of... I mean, now that, we found the Higgs and it's light, this is still in the prelude because I'm now a little bit confused. Now that we found the Higgs and it's light, does this Technicolor, is that okay with it?
No. In other words, that's where the capital T Technicolor, the brand name Technicolor, you'd say, if what you meant by that was just copying the thing straight out of QCD, that's your theory, then it would have predicted a heavy Higgs in this sense. And it much harder to see Higgs if it was very broad. But a heavy Higgs, and that's not what we get. That's not what we get. So you'd say, well, that's ruled out. So then you have to say, is that going on? Is there, in some sense, maybe we should not say it's just inspired by the, again, in assessing the strong dynamics option, you must take into account that we are looking under the lamppost of what we can calculate. Technicolor was proposed as something where I can calculate because I at least have a simulation of my Technicolor theory. It's called QCD, and nature has provided me with all the answers. So you have to cut some slack for that fact that you are looking under the lamppost, and when the lamppost theory looks different from the real world, you shouldn't be in shock. That's my point. But it leads you, I mean, the logical point is that we're now saying, okay, that was sort of some simple theory, but maybe away from the lamppost of calculability is sitting a perfectly healthy, strong interaction theory, which is, if you want, Technicolor prime, let's call it that. So that's still the code.
Yeah, okay, so this Technicolor prime which has a Higgs,
Could be like, yes, it could be like, and I should give you a name, and tomorrow I'll give you a reference because Roberto gave some lectures. Well, there's several, I'll give you a few references which try to give you coverage of that, which I won't have time for. In other words, this is now at a level of detail, which I thought 9 hours I would easily get to, but as it turns out, I'm so random that I don't. But there is a variant of Technicolor, which is called composite Higgs. Even before I talked about, even this is a brand name, this composite with a capital, this is composite Higgs with a capital symbol. There's one thing we just did. Even this is a composite Higgs. There's a sigma, it's a kind of a Higgs, and it's composite, so there you go. It's a composite Higgs in that sense. Yes, the first thought is, yeah, okay, this one theory that I looked at in the data has a heavy one. Maybe there's another one where it's right. Why not? Now, there's some. That is not, you make that assumption. You say, well, then it could be the real world. But there is some calculation you can do, which I'll try to do tomorrow, to try and test that assumption. Okay, so that's very closely related to naturalness and clarity. I will do it, so you're not just supposed to hope blindly. You should try, and every time you can calculate anything, do hold it to account. And so I'll do that tomorrow. But as an example, so you might say, just give me one example on the theory, I'll give you something under the lamppost where the composite Higgs is actually light, just like the real world. Give me one example, but I would like some theoretical control. And I won't hold you to saying that that's the only example that nature could produce. And that is called composite Higgs with a capital C and a capital H. And the idea here is to realize the Higgs itself as yet another pion. Okay. So that the pions that are eaten are pions, and the Higgs is what's called it's a kind of pion that we actually have in the real world. If a Goldstone boson in the real world would be massless if it was a real Goldstone boson. But if it's only an approximate Goldstone boson, because it's the Goldstone boson of an only approximate symmetry, then it has a small mass. So this Higgs is often also called PGB, for pseudo-Goldstone boson Higgs. Okay? That one way of understanding why a hadron is much lighter than all the other hadrons is just because it's a Goldstone boson. We're already using these Goldstone bosons to be eaten by the W, and there may be more Goldstone bosons, one of which is acting as the Higgs. And the structure of that theory is described in some lectures by Roberto, and there's a number of other views of it, which I'll give you some references for.
Okay, so with this Higgs, why can't you then just make Yukawa interactions that will give the leptons?
Good. So the question is, let's even go back to this sigma. Forget why it's light or heavy. There, I'm giving you a Higgs right there. Why can't I just write sigma L bar L in this otherworldly example that I gave you? I could have just written, y, whatever I wanted. And when this thing, if it's really such a great Higgs, and if you like, some piece of it gets a Bev, I'll get a mass, and life will be good, and we won't have a problem. And here's the problem with the composite Higgs. If you don't believe in large anomalous dimensions, if you don't believe in large anomalous, it's that secretly above the confinement scale, there is no such thing as the sigma, right? It's just quarks and gluons. So what you really would mean by this is something that looks like y, q bar q, l bar l. It's some operator that looks like, this is what it would look like in the ultraviolet. And then when you hit the confinement scale, it would both get a BEV. That would be the electroweak symmetry break, each part of it. And that's the part that would then give the mass to the lepton. And you can even have fluctuations of this, which is what I'm calling the sigma. And that would be sort of Yukawa couplings to this part. But let's just talk about the mass. Then you get this, life would be good, this would go like lambda QCD cubed, and we'd have something. But wait a second, something doesn't add up. This is this dimension 3 object, right? It's canonical. So in the ultraviolet, it can't just be this. You cannot write down at hadronic level what you want. You better try to engineer what you want at hadronic level by writing down something in the fundamental theory at the gut scale that looks like this, and it would probably then have to look like this. Right? If asymptotic freedom is reigning at the gut scale, then I can use standard dimensional analysis. If it's weakly coupled, I can use up to some logs. This is the story. And that's why gut squared. And now, if I run this down, and the enormous dimensions were doing something very minimal, then the mass that I would get would look like y, q bar q, over m gut squared. And that would look like y, lambda q, lambda QCD cube, over m gut squared. And this would still be much smaller than lambda QCD, or if you want, it would be smaller than the mass of the delta. Okay? So there's still this crisis, and so you'd still need some sort of large enormous dimensions. In fact, I should say that the Technicolor, the original extended Technicolor program, was to try and figure out what kind of gut-like theory, it's called extended Technicolor, gave you, after the various Higgsings of the extended Technicolor theory, gave you operators that had exactly this form to carry out exactly the program you designed, and it ran into various difficulties. Yeah.
Because I don't understand the significance of this definition, minimal cross and the meaning of this expansion on the back.
Yes. So first one. The first question was simply, what is the significance of the word minimal color singlet? Okay, and then the significance of this was 1 over delta expansion. So the first one is very easy to understand, but that's exactly where, I mean, and you can read more about it in Coleman, and you can read even more about it, I think, I like it better with the introduction that I gave you, but I can already tell you something very minimal that you would say, of course that's if you believe in color confinement, which is an input of this, if you believe in color confinement, then every hadron state is some sort of color singlet. Okay? So we are used to taking operators. So for example, if I take QQQ color singlet and I act on the vacuum, this has some overlap with the proton, right? In other words, QQQ acting on the vacuum, one of the things it can create is the proton. So this is what is called an interpolating operator in field theory, meaning that the operator acting on the vacuum is able to give you some state that you're interested in. Another one you may have heard of is if you take the axial currents of QCD, which are of the form Q bar, gamma mu, gamma phi, Q, and you act on the thing. This contains, for example, the pion, some momentum multiplied by the pion, and so on. So first, we have this simple thing that hadrons can be created by some suitable choice of composite operator. Now we look at these composite operators here, and we ask, what is the significance of the minimal color singlet ones? Well, if a minimal color singlet, let me call it minimal color singlet, okay, acts on the vacuum, it can create some hadron. Creates a hadron. But this is a hadron where that's easy. But what about if I do this? What if I say minimal color singlet prime acts on the vacuum? This is a little ambiguous. Does it create? Maybe it creates a one hadron state. But it can also perhaps create two hadrons. It's not immediately obvious, maybe it's a superposition of one hadron and two hadron. However, here, this minimal color singlet cannot create two hadrons, because two hadrons would mean two color singlet combinations of the colors. And there's not enough, especially in large M, that's where it becomes something which you can actually keep track of algebraically. You cannot separate the different quarks and gluons that are inside this composite operator and say, this subset is for this hadron and this subset is for this hadron, because there are no two color singlet combinations inside the quarks and gluons of this operator to separate it to two hadrons. So it's just one. So the notion of minimal color singlet is to give a sharp set of operators that are in one-to-one correspondence with the one hadron states, or to be more precise, the one blue ball and one meson states. And that's their great significance. Now, in fact, you could also say, what is the remarkable fact that the TUF 1/n has going for it? If I give you any typical composite theory, let's take QED and atomic physics, you find two kinds of forces. There's the force that holds the bound state together. Let me just call it the intra-atomic force. And then there's the force between different atoms. Let me call that van der Waals force, okay? Or the inter-atomic force. And normally the intra-atomic force and the inter-atomic force are both being made out of the same stuff. The same theory is giving rise to both of them. So naively, there is no parametric suppression of one over the other. Okay, they're equally important. Maybe one is a factor of 10 small, but there's nothing parametrically different about these two forces. Remarkably, in the large N expansion, what TUF observes is that in large N, the inter-hadron forces or interactions. When I talk about interactions, I'm talking about the interactions between composite objects. Okay? The inter-hadron forces are order 1/n times the intra-hadron forces. Now, in a confining theory, of course, the intra-hadron forces, the forces that are holding the proton together, are strong. So this is order 1, or order 4 pi, or whatever you want. That's not a good quantity to expand. But the inter-hadron forces are weak. And can be made as weak as you want by just taking the number of colors out. So the significance of 1 over n is that even though each hadron is a strongly coupled mess of gluons and quarks, each hadron is like a free particle, or a weakly coupled particle with respect to the other hadrons. So much so that you think, okay, I should just switch languages. Instead of thinking in terms of quarks and gluons, which are strongly coupled, I should think in terms of the mesons and the blue balls, which are weakly coupled. So I should just switch degrees of freedom. It's like when you find a problem which doesn't look good in position space, and you say, well, look, it completely diagonalizes in momentum space, and then you switch to momentum space. That's exactly the nature of the switch from quarks to hadrons as the fundamental description. And you might think then you're going to end up with a weakly coupled field theory, and that's just great. And you almost do. And the only problem is that, of course, the number of quark and gluon fields is finite, and hence the number of normalized gluon interactions is finite. But the number of hadrons, even if they're all weakly coupled, the number of hadrons is infinite. There's an infinite number of composite operators I can use. So what you end up with in this picture is qualitatively interesting, because it says it's a weakly coupled theory of blue balls and hadrons. But on the other hand, the distinction with quantum field theory is that the number of hadrons is infinite. And the only theory that is weakly coupled, which has an infinite number of excitations, which are weakly coupled, which are point-like, and which you can think of them each as its own particle, that we have control over. By the way, these hadrons come in arbitrary spins, spin 7, spin 8. The theory that looks like that, where we have analytic control over it, is string theory. And it is not a coincidence that string theory first emerged in history as a theory of hadrons. And then it went off as a theory of quantum gravity, and now it is returned again as a theory of hadrons by virtue of the ADS-CFT duality. So this is the significance of the 1 over n. The delta I probably should tell you tomorrow. In other words, tomorrow you will at least see the relationship of the, I'll show you the extra-dimensional construction, which you will see satisfies my words-like statement that it is a geometrization of all of the considerations we're talking about on the board. And 2, that in this higher dimensional theory that you construct, a space that is not the space we live in. In that theory, delta, so this looks like a spectrum, except this is a dimensionless number. It looks like some mass spectrum. Well, in fact, this turns out, in the 5D theory, this funny space-time that is part of the Feynman diagrams and all of that, the higher dimensional space-time that you get, this is the spectrum. So there's some abstract space that somehow emerges from the large N expansion that you get. And then, amazingly, in that extra-dimensional world, I want to show you where that extra-dimension comes from, but once you see the extra-dimensional world, you realize that this spectrum that I'm drawing here is the spectrum of 5-dimensional masses. This is dimensionless, this is dimension full, so something has to give. Well, it's 5-dimensional masses in this 5-dimensional world is actually curved space-time. The curved space-time has some radius of curvature. Let's call it R. And this dimensionless quantity is the spectrum, is equal to the scalar dimension. So I think I can try and show you that if I have time. Hence, the virtue of delta being large is just the virtue of delta being large in standard field theories. If you have a large gap of a few particles from a heck of a lot of particles, you can imagine integrating out the heck of a lot of particles and you end up with an effective field theory which is useful for low energies. And so this geometrization of strong dynamics, first you get weak coupling because you work in terms of the hadrons instead of the quarks and gluons, so they're weakly coupled, but now you have too many particles. And once you realize this five-dimensional auxiliary geometrized view, most of the particles would be very heavy if there was this large gap. Not heavy in the usual four-dimensional spacetime, but in this abstract spacetime. And once you've done that, you can integrate out most of the heavy particles and work with just the lighter particles. These are not standard particles, the experimentalist particles, but they're the particles that the theorists need to put in their theory to then calculate the quantitative. The relation of these particles to the real-world particles, I'll tell you more.
So maybe you just explained it and I didn't get it, but with n and delta, if n, the larger n is, the larger delta becomes, or they are independent?
So the question is delta, how are delta and n related? Are there constraints on delta given large n or small n? And this partly we know from examples, and the most famous example is the most supersymmetric Yang-Mills theory that exists, n equals 4 supersymmetry. In that case, to get large delta, so by the way, I've said this a little bit fast, there's some slight subtlety in that n equals 4 case, but let me not even bother to mention that. In the example that we have best theoretical control of, to get large delta, you need large n. But if you have large n, you can still have small delta. So delta is a parameter, but it can only get very large if you have large n. I don't think I find that a very plausible statement, even generally. And now, however, I'm going on pure instinct. I don't know of any proof that says in the abstract, for any example of this type that you'd ever find, that you'll never find large delta without large n. But maybe I shouldn't say that. Because look, this notion of minimal color singlet becomes almost meaningless if you're doing SVT-Higgs theories. So I tend to think you have to be in some sort of large expansion for even delta, the notion of this delta in the minimal color singlet spectrum to be well defined. For example, suppose I dropped the word minimal color singlet and I just said, let's write any local operator and write the scaling dimensions. Then we pretty much know that you can take products of operators with order 1 scaling dimension. You'll get new operators with order 1 scaling dimension. I think that is at least extremely likely. In which case you will not have a gap. And I wouldn't know what to do myself. So that's what I know about it, let's say. Okay, so talk a little bit more.